The Schwabe cycle describes the periodicity of solar activity of the Sun, involving the changing concentration of magnetic field lines caused by the convection of stellar plasma. This cycle can be observed through increasing and decreasing abundance of sunspots, which are dark regions on a star's surface. Times of increased solar activity relate to a greater number and magnitude of space weather events, some of which impact our planet, the Earth. The dynamo action of churning plasma inside the convective layer of a star is responsible for the generation and amplification of magnetic field lines. This process, known as the stellar dynamo, arises due to the movement of charged particles within the plasma, which induce electric currents that generate magnetic fields. The differential rotation of a star, where different latitudes and depths rotate at different speeds, and convection, where hot plasma rises and cool plasma sinks, work together to sustain and organize these magnetic fields over time. Sunspots are regions of a star where magnetic field is strong enough to interrupt the convection of heat-transporting plasma from the interior of the photosphere to the surface. This results in a dark spot, where the surface of the star is cooler. These structures are often visible from Earth. Despite sunspots being relatively cool regions of a star's surface, high concentration of sunspots correlate to a higher stellar luminosity. This is because sunspots, caused by tight magnetic field lines blocking plasma convection, are accompanied by faculae, caused by the gaps in magnetic field lines allowing hot plasma to convect to the surface. The net result is a hotter surface. The Sun is a dynamic system, and it goes through cycles. The Schwabe cycle is one such example, where the number and size of sunspots increases and then decreases on an 11-year cycle. During the point in the cycle when sunspots are at maximum abundance, the Sun is said to be in its solar maximum stage. Likewise, the solar minimum is the point in the cycle when there are the fewest number of sunspots. These describe the amount of solar activity. Times of greater sunspots are correlated to greater rates of coronal mass ejections, or CMEs. These events result in energetic particles being expelled from the Sun, which travel outwards into space on the solar winds. When these particles collide with Earth, they interact with our magnetic field, generating aurora. Understanding this process could be critically important to the continued development of human technological civilization. During the Carrington event of 1859, the Earth was hit by a CME powerful enough that news outlets at the time reported auroras bright enough to read by at the equator. Scientists estimate that if such an event happened today, the differential voltage between the ground and atmosphere caused by this event would fry almost the entire planet's capacity for electrical generation, as well as all non-hardened computer systems and sensitive electronics hooked up to the electrical grid. Basically, it'd be like putting all of the world's sensitive corded electronics inside of a running microwave. Current research on the Schwabe cycle includes studying how this process has changed over time by examining the evidence of modulating rates of cosmic ray impacts, leaving evidence in our geological records through spallation. Also, scientists are investigating how this cycle of solar activity occurs in stars besides our own Sun. A phenomenon similar to the Schwabe cycle has been seen in some other stars, such as Z Boötis A, but some stars do not appear to go through these cycles. This is an active area of astrophysics research.